So far, we have seen two methods for solving recurrence equations. The first method was the recursion tree method, where we take the recurrence equation and we keep opening it up or unrolling it open diagrammatically. Then we look at the running times or the level sums by summing up the costs of the nodes within each level at the top few levels. We write down what the level sums are for the top few levels, and then we identified a pattern as we continue to open up the recursion for smaller and smaller subproblems down the tree. So as you look at the level sums down the tree, you see a pattern from the first few sums, and that pattern continues down the tree. And when the recursion bottoms out, we do a summation of all those level sums to get the total running time, T of n. This was the recursion tree method. The second method we used was the master method, which applies specifically to recurrences of the form T of n is a times T of n by b plus f of n. We proved the master theorem or the master method by using the recursion tree method and by working out what these summations will be for different assumptions. These were different assumptions about the relative rates of growth of n to the power log base b of a and f of n. Depending on which of them is growing more faster, we identified three different possible scenarios, and for each scenario, master method tells us directly what the final asymptotic complexity of T of n will be without having to work out the value of T of n by this full-fledged recursion tree method. So master method is kind of a shortcut to directly help us arrive at T of n without having to go through the steps of the recursion tree method, which will take more time. But we saw that master method doesn't apply always, even to recurrences of this form. There are certain specific conditions for the three cases which need to be satisfied for it to apply. One small point I want to mention about the recursion tree method is that even though we represented the opening up of the recursion diagrammatically, for other kinds of recurrences, for some simple kinds of recurrences, we could have just opened up the recursion along the same line. We didn't have to represent the unrolling of the recursion diagrammatically. And if we get a simple enough summation by just opening up the recursion along a single line, we can arrive at the value of T of n in that way also. So the diagram was just to help us visualize what the series will be as we sum up the costs for every level. We're now going to look at a third method for solving recurrences. Well, strictly speaking, it's not a method for solving a recurrence. It's more a method for proving that a candidate solution to a recurrence equation is really the actual answer for the asymptotic complexity of that recurrence. So this is called the substitution method. What we do in this method is we guess the answer to the asymptotic complexity of T of n, and then we prove that answer as correct by induction on n. So informally, what we'll be doing in this induction proof is we will be guessing an answer, and then we'll be substituting that guessed answer into the recurrence and verify that the recurrence holds. Let's take an example. Suppose we have this recurrence. T of n is T of n by 3 plus T of 2n by 3 plus n. Now we can't apply the master method to this recurrence because it's not of the right form. So let's try using the substitution method. So we could apply the recursion tree method here, but as you'll see, the recursion tree method may not give us an exact answer, at least not very easily. So let's try using the substitution method. For applying the substitution method, we need to first guess what the overall asymptotic complexity of T of n is. So how do we come up with such a guess? Well, we'll try to apply the recursion tree method and see where that leads to for this recurrence. And as we do that, you'll realize that we can intelligently guess what T of n could be, but really in order to prove that our guess is right, we'll need to use induction. So the recursion tree method by itself may not easily give us the exact answer here, as you'll see, at least not in a very easy way. So let's start with uh, the recurrence and apply the recursion tree method by repeatedly opening up the recursion for smaller and smaller subproblems and representing all the costs diagrammatically. So T of n is the sole node in the tree when we begin this method. We open up the recursion to one level. So we have n as the root and two children, T of n by 3 and T of 2n by 3. Then we open up the recursion on these subproblems to create one additional level. So T of n by 3 will be T of n by 9 plus T of 2n by 9 plus n by 3. So this n by 3 will be represented here, and the T of n by 9 and T of 2n by 9 will be shown as the children of this node. Similarly, T of 2n by 3 will be equal to, you just have to replace n by 2n by 3. So this n will get also replaced by 2n by 3, which will make this T of 2n by 9. And when this n is replaced by 2n by 3, we'll get T of 4n by 9. And we'll have another 2n by 3 here. So T of 2n by 9 plus T of 4n by 9 plus 2n by 3. That's the right hand side if the left hand side is T of 2n by 3. So we represent these costs as 2n by 3 with two children, T of 2n by 9 and T of 4n by 9. And we can continue opening up the recurrences for these subproblems to create additional levels until the recursion bottoms out on very, very small subproblems. Now, you may see a difference between this recursion tree and the recursion trees that we have seen so far. The recursion trees that we saw so far were uniform in that the costs at every level were identical across all the nodes in that level. And that's because the overall problem was being split into A subproblems of the same size. So the size of the subproblems were the same on the right hand side for the recurrences that we've seen so far, which is why when we applied the recursion tree method, we got nodes with identical costs within every level. So we could say that the shape of the tree would look like a triangle at all times. Right? We would go on creating more and more levels. So the triangle would expand its height, but finally the recursion would bottom out when the subproblem size hits 1. And then we would have a perfectly triangular tree where every node in the interior has two children, not two children, a children in general, and all the leaves would be at the same level, which is level h, the height of the tree. But here you can see that the original problem is split into two sub-problems of different sizes. So the size of the sub-problem in this right child is larger than the size of the sub-problem in this left child. Likewise, when we open up these two recurrences, if you compare the size of the subproblem in the right child of this node, that's t of 4 by 9, whereas if you look at the size of the subproblem in the left child of this node, it's t of 2, it's t of n by 9. As a result, when we hit the bottom, we will hit the bottom at different levels. So we won't get a perfect triangle. Rather, the leaves will be at different levels, depending on how long the path is and how rapidly the size of the subproblems are decreasing along that path. In fact, it's this rate of decrease in the size of the subproblems which will determine the length of the path until the path terminates on a subproblem of small enough size. So let's in particular compare this path with this path. So this is the path where we keep on following the left child of every node in the final tree. You see that the costs are going down by a factor of 3 along this path. Whereas if you look at the right path, where we go on following the right child of every node, the size of the subproblems are reducing by a factor of 1.5 or 3 by 2 along this path. So at the ith level, the leftmost node here will have a cost of n by 3 to the power I. At the ith node along this path, the rightmost node is going to have a cost of 2 by 3 to the power I multiplied by n. So let's focus on the longest path down the tree. And this longest path is going to be the rightmost path because it's along this rightmost path that the subproblem sizes are decreasing at the slowest rate. If you take any other path, you're reducing the size of the subproblem by a factor of 3, at least at some points, if not everywhere, as in this leftmost path. Whereas along the rightmost path, the size of the subproblem is 2/3 of the previous size all the way down. So if you want to calculate the height of the tree, we have to choose that path along which the rate of decrease of the subproblem size is the least. In other words, the subproblems are not decreasing at a very large rate along that path. And this is that path, the rightmost path. So that will be the longest path because it will take the longest time for the subproblem size to reduce from n down to 1 along that path. And that's because even though the subproblem size is geometrically decreasing along that path, the common ratio here is 2 by 3. The common ratio for this path was 1 by 3. So it was a smaller common ratio. And for the other paths where we have a mixture of different common ratios, the lengths of the paths will be intermediate. So this will be the shortest path and this will be the longest path. So along the longest path, where the size of the subproblem is a factor of is basically 2/3 of the previous size, let's calculate how long it will take for the path to bottom out or to terminate at a subproblem of size 1. So at level I, the size of the subproblem will be 2 to the power I times n divided by 3 to the power I. or 2 by 3 to the power I times n. And that's because when we create the first level, the size of the subproblem was 2n by 3. When we created the second level, the size of the subproblem was 2 square divided by 3 square times n. And so one can generalize this pattern to say that when the ith level was created, the size of the subproblem uh, for the rightmost node would have been 2 to the power I divided by 3 to the power I times n. And at level h, the size of the subproblem for the rightmost node would have been 2 to the power h divided by 3 to the power h multiplied by n. And we know that when the recursion bottoms out, this size must be 1. So we can calculate h in terms of n. We get 2 by 3 to the power h times n equal to 1. So we get n is 3 by 2 to the power h, or one can say 1.5 to the power h. So h is log of n to the base 1.5 or to the base 3 by 2. So if this is the leftmost path, the rightmost path is going to look something like this. And in general, some other paths may have intermediate path lengths. Now, if the tree had been a complete binary tree, assuming that the height of the tree would be log of n to the base 3 by 2, consider a complete binary tree with this height. Such a tree would have been a perfect triangle where all the nodes except for the last level would have had 2 children, and all the leaves would have been at this height. In reality, our tree is going to have, uh, many fewer nodes than what the tree would have had it been a complete binary tree. Right? So maybe our actual tree looks something like this, the shape of the actual tree. And in a complete binary tree, there would have been more nodes filling up this region. So this shape is not exactly accurate. It's just randomly drawn, but we know that the length of the leftmost path is going to be shorter than the length of the rightmost path, and other paths will have intermediate lengths. So let's calculate how many nodes there would have been if this tree had had this height. To be more accurate, since we want to calculate T of n, let's calculate the cost of the tree had it been a complete binary tree, because that cost is going to be an upper bound on T of n for this real tree. Right? The real tree is not a complete binary tree. The real tree has an irregular shape. But if we sum the costs in the real tree, those costs are going to be upper bounded by the cost of this complete binary tree, assuming that the costs in this region are the same for both the trees. So how do we arrive at those costs? Well, let's calculate the level sums. So what's the level sum at level 0? It's n. What's the level sum at level 1? It's n. What's the level sum at level 2? It's 1 plus 2 plus 2 plus 4 divided by 9 times n. And this turns out to be n again. So you can see that we're getting this pattern where we are going on having a level sum of n. But this pattern is not going to continue for long, because some of these paths are going to terminate and other paths are going to continue beyond that point. We are getting these level sums because all these nodes are filled, so we are getting a general pattern here. But once some of these paths terminate, then the level sums won't be exactly n. In fact, at the very last level, there's going to be a single node. right? Because the rightmost path is the longest one. So if you look um, at the very last node over here, that node is going to be t of 1, but there won't be any other node at that level. So the level sum will be t of 1 there. So we're not going to have a constant level sum down this tree. But let's imagine a complete binary tree where the level sums are n all the way down till the very last level. In such a case, the sum of the costs in this tree would have been n times this height, log of n to the base 3 by 2. This would have been the sum of the costs of this triangular tree. So the actual cost of this irregular tree for the recurrence that we have is going to be less than or equal to this cost. So we can say that the actual t of n will be less than or equal to n times log n to the base 3 by 2. So we can say that Tn equals big O of n log n would be a good guess. So can we prove this? So this is just the upper bound. We'll look at the lower bound separately, but just focusing on this upper bound, in some ways one could say that our proof is already rigorous enough, but it's not as clean as the scenario where we actually had a perfectly triangular tree, as in the previous examples we've been seeing. Because here it's not clear what the lengths of all these paths will be, and um, because the leaves are at different levels, it's not completely clear what this pattern is going to look like. Although we've reasoned out that it should probably, the level sums at every level should probably be less than or equal to n. But let's try to be more formal about it. And we can do that by proving this by induction on n. So after guessing that t of n will probably be big O of n log n, let's try to prove this formally by induction on n. So we'll be using the substitution method here, which is basically uh, using induction on n to prove that t of n is in big O of n log n. So this is the claim to be proven. Now we need to be more specific than this. So we're going to say that we want to prove by induction that there exists a positive constant such that t of n is bounded from above by a constant multiple of n log n for large enough n, that is for values of n larger than some positive threshold value n naught. This is the claim to be proven by induction. In the next video, we'll go through the proof.